So today we're going to be talking about school biomass boiler projects, a 2020 review. There's two main public schools that Mark Froling will be talking about. And first I want to tell you just about Froling Energy is that we are a mechanical contractor who's focused on installing the latest high-tech biomass boiler systems, the most efficient, the lowest of emissions. That's our focal point, to do it right. We work on schools a great deal, but we also have a lot of commercial buildings, industrial buildings, and multifamilies, as well as single-family homes. So that's our big focus is on the commercial side. So as a self-performing contractor, we're doing all kinds of work on site. We're not going to put in windows or doors into a building, but we very often will build a brand new boiler building if that's what you want us to do, because it's all boiler focused. It's all boiler system focused. And we'll hire subcontractors, say for controls or different things to be done. But otherwise, it's done controlled by Froling Energy. So it's a one hire. It's like almost like a GC. But again, it's just in this one aspect of a project or a singular project that is simply about changing out boilers. We do a lot of technical consulting on biomass boiler systems, and that's a very important part of what we do, where we're talking with architects, engineers, building owners, interested parties, where we're just talking about general feasibility, getting down into specific design and value engineering, and talking about costs and ROI and so forth. There's a lot of grant applications that we work on as well to get things pushed through to be sure they're fully funded. We manufacture precision dry wood chips, which are screened bullwood chips. They're dried to 25% moisture content. And with that size and with that lightness of the chip, we can deliver them by blower truck, where you can see these silos. There's some 25, 30 feet in the air, and these big trucks just blow it right up and in. And it makes for a very economical installation, which is what this is all about, to try to get things to happen. So today, again, we're talking about schools that we worked on last year. Mark Froling is the president of Froling Energy. He's been doing construction and construction management for a long time here, and he's been 25, 30 years here. You've been working on this kind of thing, and he's also part of our team here in so many different ways. He's the leader. He does a lot of project management. He does a lot of work on installations. So many different things. So Mark, you can tell a little bit more about your background and your story if you like, but we've been working in this biomass area for 12 years or so, where we've really evolved a lot of our own knowledge, but we've also evolved some of the techniques that are used in the industry here in the northern New England area. So Mark, welcome.
Thank you so much, Jim. And I'm just going to ask, Jim, can you see my slides?
Yes, I can.
Okay, perfect. Then we're in good shape here. So my name is Mark Froling. I'm the owner and operator of Froling Energy, and Jim has done a great job with the introduction here. We are a company that does many different things, but it's really all related to biomass. So as long as it has to do with a biomass boiler, we'll take on more and more of the combined job or of the holistic job. But in most cases, we actually are just boiler makers, where we put the boiler in and then provide fuel and provide the service after the construction is done. In some cases, we will do the boiler house or central plant. In some cases, we actually own the boiler plant and sell the heat. And so we've done many different forms of business with our clients, and that has worked out quite well. But the most common form is just the standard contract for putting up a boiler plant and then selling the fuel after the fact and selling the services after the fact. Today, I wanted to actually just kind of go over two specific sites, Johnsbury School, which you see here, and also the Campton Elementary School, just a little bit further down 93 on exit 28. in a very small town, but a lovely little town that is very New Hampshire. And so I'll start with this St. Johnsbury slides here first. And I imagine if somebody has questions, they can just chime in, or we can take them afterwards. I'll let Jim kind of dictate that as we go along. So the St. Johnsbury School, it's you know, pretty far up north, and we had looked at this school maybe 5-6 years ago, and I don't think there was much interest there, or maybe the budget wasn't there. And then this project came around again this time around. I was actually contacted through Kohler and Lewis. They were the mechanical engineer of record here for this particular job, and they approached us with during their design phase and their feasibility phase, and we worked with Kohler and Lewis, specifically with Roy at Kohler and Lewis, to get to the bottom of it, suggest things, recommend things, and then later on, when we bid on the project, because it's a public project, so we have to win the bid or be awarded the bid, and so we had to come in as the low offer here. And so that is what you're looking at there is what the project looks like now, and it looks quite similar to what we designed it at. Here's the front of the school a little bit, or the corner of the school, and the sign on the road. It had been using 48,000 gallons in the year before, and is now projected to use 450 ton of dry chips. It's a little bit less right now because we're only 5 months into it right now, so we still have one more. You know, I adjusted for it mathematically, so after it's all said and done, it will top out right around 450 tons of dry chips. It'll provide them roughly $60,000 in savings, and that of course depends a little bit of where our price for the dry chips are, or the gallon price is for the fuel oil. But that's certainly in the vicinity of the $60,000 in savings. This was actually one of the very first designs. This is just a design that I had modeled for the school. That was before we were awarded the project, as part of the design phase, to make it presentable for board meetings and for the owner to review, to see how that would look. So when I go back a couple things, it looks quite similar to what we actually proposed, which is not always the case, by the way, but we try our best to model things out the best we can, and then implement that to the best. But here there was quite a large design team involved. There was architects and engineers and the whole slew of design professionals on the front end, which we don't often have on smaller jobs or more direct sold jobs. We actually do a lot of the design and sort of design work, and but in this case, this was really a very well worked out job, so there was not a lot of sort of design from our end needed. Roy did a really nice job here on the overall the engineering and also on the design, and it's functioning very well. And the reason why I know that is because, in fact, we have not many calls. In the beginning of the jobs, we always have a few calls, but they've tapered down by now, and so it's working quite well. I was up there yesterday taking these photos, and it was nice. So part of the design phase, though, we have quite a bit of engineering on our end, where we work out the boiler placement, the floor plans, the whole mechanical system, so we know that materials and equipment fit into the room. And in this case, I worked with Kohler and Lewis to make sure that we had a design that fit their building, because there's so many different firms here involved in this whole project. We're not the only construction firm involved here. There's masonry, there's electricians, there's plumbers, all along. So not only do we have, of course, just a boiler plant, which you saw on the prior slide, but we also have equipment that's oftentimes, not always, but oftentimes custom made. So we're directly involved kind of in designing the buffer tanks just the way we like them, And so we have specific designs for all of these different sizes that we've used over the years that we like and that we know, and then we can adapt them if we need to have configurations of where the pipes come out, if they're top piped or if they're side piped, or if you need a 45 configuration, depending on the architectural details of the building. So it's quite specific, and it surprises a lot of people that we have to actually put in quite a bit of very specific front end work on these projects. Even on the silos, you have to really work it out when you have a site that's as constrained as the St. Johnsbury site. We only had one approach for the staircase, and we had to reach the very top, and then we had a banister that had some conflicts, so it's incredibly tight to plus or minus 2 inches here in terms of how this staircase can be configured. So it all had to be modeled by this company to do that, and then we help. So it's quite common that, of course, the mechanical engineers are much more experienced than us in terms of figuring out the mechanical system. But because the biomass systems work a little bit different in the terms of that they need longer times to start up, and they need much longer times to actually stop, because there's a huge amount of when there's a turn down in the distribution system, there's still a tremendous amount, or there can be a tremendous amount of fuel in the boiler. So there needs to be a battery in between, and we call that the buffer tank. And so the design is actually really interactive between us and the mechanical engineer, where we show them this is kind of what we need for our appliances to work, and then they help us integrate it into their overall mechanical plan. So this is actually sort of a drawing that I might work with Roy, reflecting like, this is how I know our system will work and all of our sensors will work for the boiler to operate optimally. And then he will take that and work it into his system, so he knows the distribution system in the school will work, perform at a high level as well. So that's sort of the interaction. You see all that work beforehand before we actually even get to in. We do a little bit of modeling, as I mentioned before. That's just to show pictures, because not everybody can just look at a floor plan. So there's some pictures involved as well to see, does it aesthetically fit with a school. In this case, I think the architects actually did a really nice job using the existing brick from the school and really tastefully integrating it into the campus. I love showing up at this campus and seeing this. I'm quite proud of it. And I put in a sign, not necessarily thinking that this sign would end up on the final build, but it did, even including the lights. So I was quite surprised at that. It really looks quite like that. And of course, this is something that I would work out with Roy in terms of the exact layout. So his mechanical systems work with my mechanical systems, and all the maintenance clearances that we need along, and the safety clearances and access to parts and pieces that we need to replace over time if needed. Here we are after the entire project was built. This is actually the commissioning day, where we're just filling up, we're testing motors, and we're filling up this silo to actually test the boiler. And does not look like it has, I don't see a puff of smoke on the stack yet, but within a few hours of this fill up, we were actually curing the refractory of the boiler. Here, and now you see the finished product here without the truck standing there. It's really beautiful design all together. And you see the access when the truck backs into this spot to deliver the wood chips, which is done pneumatically. They back up. There's maybe a 20-foot hose that goes right to the silo. There's a picture of how that connects. Here's from the other view, so you can see the fill line very prominently right in the middle of that, and you can see the door to the access, the ladder to the roof access of the silo. This is very important to kind of consider that on the front end. These things for the first couple of years, we actually had ladders to go up, but we have noticed in the meantime that we don't do the ladders anymore, because we noticed that the truck drivers or the delivery drivers do not necessarily like to go up on a really pretty day, or even on a sunny day for that matter, up these ladders. So now, even though the ladder is the staircase is much more expensive, we put these ladders in so we get better feedback from the truck drivers. They don't mind going up this nice staircase and looking in and kind of checking levels, because we effectively, our company acts like an oil company where we maintain the levels, and so the school does not have to always give us a level and say, hey, please come up here. We actually deliver the fuel, check the level, and make sure that we need to come back in a week or two. The drivers typically dictate that to the service department, and it gets scheduled in like that. So over the first year, we typically establish a good schedule that we can use for the following year. This year was a little bit unusual because, in fact, we used more energy than in the past because of the ventilation that was required because of the COVID. So that's unusual. Usually we don't see that. We usually see a good size energy reduction, but it's of course assumed this year that a lot more air has to be moved, and we're seeing that in this particular project especially. So this is a picture of once the overhead doors, in, we had to get the boilers in through the overhead door, and that might have been a little bit bigger. We only had 1 inch to spare to get that in, so it was a hard install, but we got it in there and assembled nicely. Here's an important part. A lot of wood chip boilers, mostly green, but even some of the dry chip boilers that are being sold are still being sold without the automatic ignition. Part of the ease of operation for institutions is that you want to have something that's fully automatic, and having an automatic ignition device on these boilers is really critical. Now, of course, if you have green chips, they're very hard to ignite automatically. Typically, that's done a little bit differently, but in this case, you have dry chips. You only need to blow hot air. This is about 400-degree hot air at the dry chips for about 5 minutes, and then they light up just like that. And if it's just a reignition after a couple hours, the igniter only goes in for maybe 1 minute just for safety. But during the winter, this boiler more or less ignites, turns off, ignites, and turns off over and over with very short ignition cycles. So because the refractory stays hot for several days if you don't open up the door, so there's still incredibly hot inside the boiler after it goes out, let's say at 5 o'clock or 6 o'clock every day. This boiler turns off because the load diminishes so much after the setback period goes into effect. Now, after in the morning when it turns back on, maybe 4 or 5 o'clock in the morning, this boiler starts up, and within 5 minutes it has a really good flame going, and the burn the grate is being filled up, and it goes into operation. And the operation is quite good right now. Since we have tuned it in the very beginning, it wasn't tuned so well, and I don't remember the exact thing that was wrong with it. But it, oh yeah, I just remembered that it was actually a gearbox that was not sized quite right. So in the beginning, we had the load was a little bit undersized of this boiler, but the manufacturer, of course, made good on the gearbox, and since then it's been running 100%. At your school at 100%, no problem. Here's another features that are really important for the automatic operation of a good boiler. So if you do not have the soot blowing action that's automated from the PLC of the control cabinet, then you have to brush these boilers out a lot more frequently. And that is done, of course. People sometimes don't have the automation and they need to brush these tubes out, but this particular boiler can be run for half a year without brushing, and the tube cleaning is just incredibly effective. There is almost 100 tubes in this type of boiler, and so we have 6 soot blowers or 6 solenoid valves here that are of course I don't know, maybe 15 or so of these tubes are cleaned by 1 solenoid valve here. I'm not sure what the exact dispersion is, but it depends a little bit on what zone they're in, and but it's all automatically done, and that is the key to a good operation here. Give me just 1 second. Yeah, I'm on the computer. You good? Yeah. Sorry about that. where was I? So this is a key element to operate this boiler automatically. The front of the boiler, check for operation. Here's the automation that makes this all work with every boiler. This is, web-enabled boiler that you can see from anywhere. When we run into trouble, the manufacturer is from Switzerland, and they will come in fact, help us with tuning when we needed to decipher why we wouldn't get full output in the beginning. They were actually, able to test and see that the feed screw there from the stoker motor was just not transporting enough fuel in, and so really by electronic function, they were able to discern what was wrong with it, and it's quite helpful when you have long distances in between. Also, now it's tuned in through their BMS, and so their local plant manager can quietly see all the boiler functions and the temperatures and see if that is in good operation. Here's some of the other safety features that are also quite key. So you have these door switches. If somebody manually opens these doors during certain times, they can be opened, but it actually puts the boiler into an idle and goes into a safety standby, so there can't be a blowback or whatnot. During critical times, if you open up the door, it's actually just locked out. So as soon as you pull on the door, it will insert some lockout mechanism because it knows that it's not it doesn't have the right negative pressure. So these kind of safety features are the norm in Europe. They're not needed here actually for by certification or anything like that, but they're quite nice to have. Sometimes they become a little cumbersome just because you have to go through a procedure, but in fact we're quite happy with them because nobody gets burned and nobody gets hurt during these operations, and as soon as people are a little bit used to them, they're very functional safety devices that make a lot of sense. Also gives you some feedback if you don't quite close the door. It knows it because it's not latched in. And the same with that burn back gate. In the central picture there, it's a little bit hard to discern, but there's a safety valve. So if you have any kind of temperature rise in the back end on the stoker side of the boiler, then in fact you have a safety valve that can not only douse it, but it can close it with a pneumatic valve. And so the pneumatic valve then activates, closes out the fuel, and everything is safe, so it cannot burn back into the store chamber. The silo design is actually a little bit harder than most people realize. It just looks like a normal farm silo, but in fact, this silo is really picked for many different reasons. We used to use corrugated silos, and we were a little bit unhappy how the additional surface area of the corrugation, in fact, created a lot more friction of our material, and so the flow of the material through a silo was diminished. And so that friction coefficient that increased really actually made it harder in the winter months to work. Also, you have a little bit of increased wall surface, so in terms of getting colder, that also made a difference. And so we've seen a lot better performance with these flat wall silos. And there's some nuances on these silos that really make them work quite well in the way that they're assembled, and also in the way that you have them sealed on the bottom edge. So these are actually cast in place starter rings, and that makes a really good watertight seal, because you do have quite a bit of water coming off the silo during rainfall. And so we've been very happy with this design of this bin. It's not always easy to get. This manufacturer is quite busy and hasn't been the best supplier, but nonetheless, it's not 100% organized here. But on the left-hand side, you have the flue gas fan and the lambda sensors, so the O2 sensors. So there's some, the boiler really does drive to about, on the dry chips, targets about 10% oxygen. And in general, achieves that quite easily. It's not a problem to run at 8 or 10% oxygen. Depending on your moisture content, you really tune that in the beginning and then you set that. The boiler itself mostly drives off the combustion chamber temperature and then uses on the right side of the picture, you see your flue gas recirculation. And when you have dry fuel materials such as that we have, we oftentimes have 20 to 25 to 30 would be a pretty wet chip for us to deliver, but we are hovering at 25% most of the time because it's the easiest to store outside during the very cold winter months. And it's also brings us optimal sort of energy density in there. And so, but the recirc fan is really important for that. So it is taking oxygen depleted flue gases and injecting them into the primary air, and thereby effectively not quenching, but sort of diminishing the temperature inside the combustion chamber, rather than just reducing fuel. Or I've seen boilers that add water just to diminish the combustion temperature, but that is one way to really control the temperature in there. And really, most of the time we're running about 700 C in there, and that's optimal. And once you go over 750 or 800 C, then you're making glass in there. And then the ash fusion temperature is, at that right around 800 or 850 C. And so what we have noticed, anybody that really supplies the flue gas recirculation, they can control that and can control that tightly. They do a really good job with complete combustion. You get very good ash content, you get very good efficiency overall, and good results. And then all your maintenance goes down as soon as you can control the overheating of the combustion chamber. You don't get the clinkers, you don't get the stagnation of the ash inside any of the material handling systems as well. And there goes, after everything gets warm, of course, the easiest part is actually moving the water into the customer's distribution system. And that is that. The second project here that we have, and I'm just going to check time here. We're in great time here. The second project that we have had this year is the Campton Elementary School, and it will look quite similar here. It had a little bit less load, actually quite a bit less load. It's half the size, and actually because the boiler was actually part of a performance contract here, there was quite a few energy savings achieved in this project. Not only did they reduce the overall electrical usage inside this building by close to 20%, also some thermal loads were diminished as well by better control. So throughout the building, the controls were changed, automation was put in place, and of course timers and sensors were placed so to reduce further energy use. And so that has made that a pretty successful job overall for the owner here. This is, I think, the second job that we have done for the same SAU up there. The other one next to 2 exits down from Campton is Plymouth High School, and this is the same SAU up there. And then they have been a pretty interested owner, and they have a great plant manager and also a really great operations manager here to really get after these boilers, because solid fuel does take a little bit of extra time and a little bit of extra effort over liquefied fuels or gaseous fuels. It's just a solid material, and so you have a lot more solid waste as well, or the ash, I should say. And so that just takes a little bit more doing. There's more material handling versus pumps, and there's more ash extraction versus soot in a chimney and things like that. So but having said that, these guys are quite experienced in sort of wood burning, and they seem to really take to it. And it comes down to the local operators, and I'll show you one little detail that shows me that this person really cares here. This project here, Banwell was involved as the architect to put this together. So in this particular case, we actually furnished the entire central plant with the silo and some other alterations. We the owner had some was interested, of course, in putting the wood chip boiler in, but they were also interested to get a little bit out of it for the school itself. So this boiler plant was situated right next to a little hillside where the sports fields are, and so it's just on the downslope of the sports field, and so they wanted to also get some storage out of this. So we increased the overall size of this building to accommodate the owner's wishes to put in a little, I think they put ball storage and outdoor gear storage for the sport, when the sports field gets used during the summer months and the fall months. So again, this is sort of this is our design that we made for the owner, and then the engineer basically took our design for this implementation. And we worked all the way. We had to actually do a pretty large pipe run throughout this school here. I think the overall run was from the central plant to the old boiler room was about 400 feet in total. So there was some underground work and some above ground piping work. And here again is also us doing the interaction, the Schmidt boiler manufacturer that manufactures our boiler equipment and also the material handling equipment. Then we coordinate the physical space from the architect with the boiler manufacturer and also the silo manufacturer and also the underground utilities. So it's a tremendous amount of coordination gets into a project summed up on one page, but nonetheless, it sometimes can take an entire month to get to the stage where you can sign it and then they build it and then you kind of own it, because if you haven't done your homework, then that's not quite right. And so, this is another picture from the architect showing, so we create sort of our equipment plan, and then the architect works with our equipment to build the building around that, but also then accommodate the owner's wishes of the upstairs equipment storage for the sports field. And here is the plant, very much like the drawing shows as well. On the right-hand side, there's a little retaining wall because the backup fuel was natural gas, propane gas. And so the owner, also switched some appliances to, around as well from electric to gas. And so they had a good use for, I think, maybe 5 propane tanks. And so there's a little utility area now behind that fence that is for the gas tanks. And here there's a little bit from the other side. You see a man door, the overhead door with a boiler right inside there. Here is the silo with a nice plywood door that is yet to be delivered, and it's been back ordered for almost 6 months. And this gate is really important when you're working in a school. That's why I kind of showed it off a little bit. When you're working in a school, young kids tend to want to go right to the top of the silo, and so you have to barricade the first 6 or 7 feet here with some really good wire mesh, so you can keep people off the staircase, because ultimately a little bit of vandalism happens or things like that, and you just don't want anybody to go up there. So this is really key. We do this after the fact that it does not come to silo supply, so we have to then step up and get this custom fabricated as well. Here's a 400 kilowatt boiler. It's a little bit smaller than a St. Johnsbury boiler. It only gets a delivery about every 2 weeks at best. Like I said, the school has put a tremendous amount of efforts into reducing their own overall footprint here, energy footprint, and has really seen if I convert it back to the original gallons, they have actually, even though it's a COVID year and they should be using it quite a bit more like all the other schools are seeing, we are actually seeing an 8,000 gallon less usage. Even we're using wood chips, but I'm converting it to gallon because a lot of people know a little bit more about the gallons. But this was a 28,000 gallons, and now it's the equivalent of wood chips to 20,000 gallons or 21,000 gallons. So it's quite a bit of savings just through the energy savings on the thermal side. Very impactful, and it's the best of both worlds when you can save energy, and of course you're saving also dollars as well. Saving a tremendous amount of cost, and that can then build. You're more or less building these projects out of the savings that you are creating. Again, it shows the recirculating. So when we use these dry chips or when we use pellet boilers, and so we still have almost 200 pellet boilers out there, and then we have about 50 of these chip boilers out by now. And when we use these chip or any dry fuel boilers, we have to have recirculating air on there in order to make this all work. So here on the left-hand side, that's another picture of a little bit different configuration, how we're recirculating that. But that is right there. And then on the right-hand side, you actually, one thing that I did not point out in the first school here is you have automatic ash removal, and that ash gets removed into that front end into that front end container, and then in the rear end. So the front container, ash container that you see here on the right-hand side picture, is actually for the grate ash, and that moves to the front of the grate and then gets excavated out or pushed out with an auger. The rear ash container actually comes off the cyclonic collector on the rear end of this, even though the boiler doesn't look like it has it, but it has it encapsulated inside the jacket. Is a pack of cyclones, and it does a tremendous job. It's really one of the better cyclone designs that I've ever seen, and it does a tremendous job collecting the fly ash that's going through there. And we have been testing. This boiler did not get a test because it's too small, but we've been testing these boilers, and just with we are easily can meet compliance here in this state just with the cyclone staying under the EPA guidelines or the NHDES guidelines. Without much tuning or anything like that. I mean, of course, we do tune it to be optimal, but we have been under not just New Hampshire's regulations, but even the tighter regulations for Massachusetts as well. No problem at all thus far. So it's just all very good news, and I'm quite happy with that kind of performance. And it's performing well because when you're emptying out the fly ash and it is just absolutely powdery, you've done a good job separating out the fly ash from the gas stream. Is a little bit of the material handling that I wanted to point out here on the right-hand picture. You can see that top auger comes out of the bottom cyclone. So there's a slope to the cyclone, and out of the bottom of that is just a collection auger that drags it out essentially and then drops it into that ash bin there. That's just what I talked about. On the left-hand side, the two orange augers that are coming out are actually the ones coming out from the silo. The top one in that picture is the material auger, and the bottom one is actually the drive shaft that drives the spinner inside the silo. The silo gets unloaded with a spinner. We call it the horizontal discharge unit, and that spinner is there's several different designs. We have found that this design is really a very stout and reliable design because it has two motors. Sometimes the spinner and the augers are actually combined as a single unit, and then there's basically a right angle gearbox that from the auger that drives the spinner. But we like the two motor application here because first of all, it's a little bit of redundancy. Also, you can, if you have material that bridges more, you can increase, in fact, by the controller, your cycling time of that spinner. And so it gives you a little bit more option in terms of how you want to run that. And we have come into situations where we have very, very material that is easily bridged in the silo through compaction or through just the way the material comes to us. And so the advantages of this two auger system or the two drive shaft system is quite important to consider early on. On smaller boilers or more fluid materials, the single shaft operation is absolutely fine. But when you get into sort of industrial usage, you really need to consider this two shaft operation to give you more flexibility and also to handle a larger variety of fuels as well. And at the St. Johnsbury School, the backup boiler was in fact inside the original school. It was the original boilers that had been left there from 20 years ago when it was first installed, and they were still in good enough shape to back up the biomass boiler. In this case here, the boilers were really end of life. I think they were close to 40 years old by now, and they were failing, and they were not replaced. They were, in fact, the old boiler room was more or less gutted and is being used as just a sort of a distribution room now. So it's a lot cleaner and a lot more roomy, and we have put some of the controls for the schools in there, and so that room is being used a little bit differently. But here we have a Lochinvar boiler that's being used as a backup. It works very well. It's the first time that we've used this kind of this brand, or this not this brand, but we've used Lochinvar quite a few times. But this model is the first time we use that, and it is a very, very easy machine to understand. Works very well, has been very reliable. It does not really come on hardly at all. I think we ran out of fuel when we didn't anticipate a cold snap, and so it popped right on, and it was no problem as well. It's always good to have 2 boilers, even if you're backing up with another wood fuel boiler or several different fuels. Sometimes we have 3 boilers, but in schools in particular, it's nice to have 2 boilers at a minimum to do that. And then that little picture right in the middle, top middle there, that's a little bit to show you what it really takes to run it. When you see these kind of things, that every day he does a physical check, checks around to see if how the fire is running. He does a visual check, and once a week he rakes it out, and then he notates it down. And that's just like, that's so perfect. When I saw that, I thought that this boiler plant really will have a really nice life, because when you get after a boiler like that, it in fact will give you respond very well. It will not break down very often, but if you neglect any kind of machinery, of course sooner or later you'll be on the short end of that stick. But I can see right now here, these guys treat this boiler plant very well, and have it super organized, and we're performing really well there. So I think the owner is really pleased, the operator is pleased, and we are really pleased to see that. So I have just a couple more minutes here to talk about what's to come. We are actually just in the very last phase of moving. We just moved to a new location. You see a little bit of a picture here. It's a new location in Keene, and we have been making our chips and delivering our chips from Keene, New Hampshire now from about, I think we started making our very first chips here in November. We moved our inventory from the old plant to the new plant here in August, and so we've been delivering here since August of 2020, but in fact production turned on maybe just after Thanksgiving. And it's been going great. We have a really wonderful facility. It's fun to be here, and we're working out some new stuff that's new to us, because we're now sort of stepping it up into the next phase where we are using high pressure steam. That's not all that common in central boiler plants, unless you go into industry. And so we're using high pressure steam with a steam turbine, and so that's something that we're working on to kind of really get our head around and offer that to other clients with wood driven operation. And so we're excited about that. We are also working on a project where we have a wood boiler that drives a heat driven chiller, and that will be online here within a few months as well. So we have 2 really I wouldn't say cutting edge, because heat-driven chillers have been around for over 100 years, but it's sort of the new breed of heat-driven chillers that's coming around. It's the Japanese unit, so we're really excited about this Yazaki unit, where we're saving the owner also some, not just some energy, but actually we're saving the owner some cash here by running it off the wood chips. So it was something that we've been looking for a long time. So we have our first sort of cogen heat and chill, or heat and cooling of a wood boiler, and then we have our first cogen of the high pressure steam. And then the last one I just mentioned here is our improved dry chip production facility, which will hopefully deliver and manufacture chips for many years to come here. And with that, I want to turn it over to questions that people might have. I don't know if Jim, if you want to moderate that a little bit.
Yes, I think if somebody wanted to open up their microphone and take their turn, they can do that. But I've got a number of written questions that I'd like to ask. So let's start here. It says, Bales Energy, or Bart Bales says, can you give us some guidance about proper sizing for a biomass boiler? Number of questions in a row here. So sizing, and for the buffer tank for a boiler and a load of a given size. And then for school, was the boiler sizing based on school design heat load by matching the capacity that had been there, or some other methods?
Yeah, okay, good. So the sizing in general, of course, can be done in many different ways. And I will go through a little bit of the history because it really does boil down to the longevity of the boiler and operation of the boiler as well. So when I started first installing biomass boilers in 2008, so a little while ago, we tried to be really fiscally responsible and really undersize the biomass boilers and then put larger backup boilers in order to kind of basically stretch the dollar as large as possible. But I will tell you that my experience has been that really sizing it at 70% is so 75% or 80%, but maybe not at 100%, because right sizing it, you don't want to, I mean, you can do that if that's your only appliance. You certainly should right size it and then maybe have another smaller boiler beside it. So, but I don't necessarily believe in undersizing it so much that it runs 100% of the time. If you do that, you really need to choose the right technology. And early on, we did not have that experience to choose the right technology. We undersized quite a few boilers and we sized them with what, too light duty of a boiler. If you're running a boiler 100% of the time because it's undersized, you need to get a very industrial boiler in this. You're going to pay a tremendous amount of money for an industrial boiler like that versus a light machine that you put in a small commercial. So, but if you put sort of the 70% or 75% boiler in of the design load, you will find that now the boiler will get a little bit of rest time here and there, and you're not going to get 4,000 hours during the heating season of operation. So it's a little bit about choosing the right appliance for the right application, and it is even hard for me. That is one of our main criteria in the beginning. So we take great care in sort of choosing, okay, looking at it, do we have a person that can really take care of it? Or do we need 100% automated operation that's really robust because we don't have somebody that really can, specialize in raking a grate? Because that's definitely an operation that, for instance, if you only have a janitor taking care of it in a school, which is quite normal now because the schools have been sort of taking away all their funding, so they're reducing staff and more, and so we're seeing, and that's an unfair request to have a grate raked on a, let's say, weekly basis by a janitor. That's an uncomfortable situation. So then you have to kind of design it like, okay, let's get a moving grate in there, let's get full automation in there, make it more robust, and make sure that we have a boiler that only really needs to be touched twice a year, and then we can do that by service, but it will cost more. So there's a tremendous amount of experience that goes into it. I wish that there was a rule of thumb you can just publish, but it's not. It's more coming from experience. Is this the right boiler for that? Of course, the lighter duty the application, the lighter duty a boiler can be. And so, but I would say undersizing it is quite risky in terms of operational costs. What we have seen where we did undersize boilers, the boilers do work, but the operational cost in terms of wear parts and spare parts and in terms of cleaning and whatnot just goes up exponentially. I have not seen that being worth the while. It is much better to size the boiler at 70% or 80% and they get really good performance of that. Because I will tell you that most engineers are actually quite conservative on sizing the boiler. So when you're sizing it at 80%, you're probably a little bit closer to the actual real load in fact. And so that's been sort of my experience. And, you know, it is really a little bit of experience-based decision-making rather than calculated decision-making, unfortunately.
So you're saying that you are basing let's say you're going to this existing school. In both cases, you had existing schools.
Yeah.
So what do you use to try to calculate what the design load is? You can look at the old boilers. You can maybe consider some of the new energy savings. What do you do?
Well, most of the time we're working in commercial projects where we have the load given to us, the design load given to us, and so from engineers, we can also deduce it based on their record keeping, certainly from fuel usage and things like that. In the meantime, we have hundreds of boilers out there, so we in fact can look at how one type of boiler performed versus another at this gallonage, just because we have so many schools now in play that more or less I could tell you just by looking at the school. I don't really need to do a lot of calculations. I can tell you most schools in New Hampshire more or less have a load of a design load of basically 30 to 35 BTU per square foot. You know, so it's quite easy to kind of look at these numbers and make sure that you can check them a little bit here and there, but it's easy enough to see to kind of average them out. And since we've done that, we've gotten much better results in the last 5 years. Just from all of our prior experience, we have really seen a tremendous amount of drop in terms of service calls, and also in terms of repair parts and whatnot. And so we are getting into more commercial industrial boilers, but we have been able to to really design around the operations much more carefully to limit sort of the risk exposure to ongoing problems and shortfalls in outputs and things like that. So I've stayed away from the designing of undersized machines. I do not like that anymore, just because of the wear and tear on these machines.
Okay, we've got Bill is asking, on average, how many ignition cycles do you see a day? Is the boiler modulated so it can reduce the output based on load to reduce ignition cycles?
Yeah, on these two boilers, the smaller boiler at Campton, I will tell you, goes on about 3 times a day. That's about it. It goes up, it goes down, and it goes into a little bit of a maintenance mode as well for, I think, maybe 20 minutes or so. So it has the ability to keep a flame for a short amount of time. And but it really only uses the igniter at max 3 times a day, even up until yesterday, So it turns off. When it goes on, it's always on for several hours. I will tell you that at St. Johnsbury School, where that boiler is really cooking, it can go sometimes 3 or 4 days without an ignition. It is not much cycling. It turns off it turns off once a day just because of the setback period. That's right. Because the load drops so quickly. It probably could maintain the nighttime load there, but the load drops so quickly when people leave the building that the load drop is too quick for the boiler to stay on. So it simmers down, turns off, but it doesn't really turn on for many hours. It turns on. I think the setback period ends at around 4 and comes back in, but it does not reignite during the day. It's of course, I haven't gone there today. It's a very warm day. Maybe on a warm day it does reach that, but it has, in general, it has a good 4-to-1 turn down, and then it has that little maintenance cycle as well.
The buffer tank probably pitches into some of that
Yes,
capability, huh?
and the buffer tank as well. Yeah.
So Bart asks, so running the boiler temperature cooler improves efficiency. Very interesting. Can you tell us more about why this is? Something you said earlier, I think he's referring to. So
Cooler. I don't remember saying. Oh, I think he's referring to the combustion chamber temperature. It's actually it's not the boiler efficiency. We're talking about overheating the combustion chamber. So when you are, so the boiler is, controlled to run at around 650 or 700 degrees C in the combustion chamber, and the recirc air, so this is the exhaust air, is injected back in, because after a little while, the refractory, everything wants to actually go higher and higher in temperature because you're putting more and more fuel in. So it tends to want to just kind of run away with it. But in fact, the runaway function is controlled by inserting this oxygen depleted exhaust air back into the combustion process, and so thereby diminishing the oxygen and then cooling the overall combustion area, and but still able to keep up with the loads. But that's just a method that not every boiler is capable of doing that. So few boilers are able to actually handle dry fuel. The wet chip boilers are much easier to handle because it has a tremendous amount of moisture in the chips that it's always constantly driving off. And so that drive off principle of the moisture can be used for cooling, so you don't have the runaway effect. So it's actually a little bit harder to make a boiler that burns drier fuel. And the drier the fuel, the more complicated it gets. And if you get too high in temperatures, then you have the ash fusion problem where you get clinkers. And that, of course, creates havoc in your ash waste stream. So that was not so much about the boiler efficiency itself, the overall boiler efficiency, but it's certainly the efficiency of the overall operation.
Mark, can you tell us about the domestic hot water provision for Campton and I guess for St. Johnsbury as well? What are they doing?
Both of these guys have indirect functions for domestics. So they are using their, well, in Campton, we used brand new ones. We put the new superstores in, and then they have recirc. That's very normal for sort of elementary schools and high schools in New Hampshire anyways. And so they're running indirect in the winter times, and then we also made a provision that they, with hand valves, can switch over for summertime use, and then they have a hybrid heat pump type water heater that they can use just for, let's say, the 3 summer months where they don't want to have the boiler on, or 4 summer months where they don't want to have the boiler on and not run it indirect. But in general, the buffer tank can store a tremendous amount of energy. So even if the boiler turns on only once a day, it can actually store enough energy for the domestic hot water throughout the school year. And we've seen that in many different places where they just run the boiler all year. But in the summer, they tend to turn it off either for service or because they don't want to be around for the operation. And so then they typically have a backup water heater. Some people have a gas backup or things like that. We have even seen other electric backups. The heat pump backups are becoming a little bit popular, but we've seen quite a few problems with those heat pump water heaters as well. So they're sort of popular, but they're kind of going out of the popular mode right now just because they're not quite as robust as sort of a nice indirect tank is obviously very robust comparatively. So that's how they're handling it, indirect during the winter times, and it's a very easy operation with just a coiled tank.
Okay. What is the typical thermal efficiency of the Schmidt boilers with the recirculating air? Is there a thermal burn efficiency, thermal efficiency? I think that's what we're saying.
Yeah, the overall thermal efficiency at the 25% is about 80% efficient.
Okay. He wants to know what's the square footage. Dick wants to know what's the square footage of the 2 different schools.
I would I would have to get that to you. I don't have it off the tip of my tongue right now. St. Johnsbury School is quite large. It's a large school. It's unsuspecting, but it's a larger school.
It
It
looks
uses
like
a lot of fuel. It's also in a northern climate, and it's propped up on a hill, so seems like that heat exchange is pretty tremendous up there. But they use fuel that we usually don't see associated with a high school so much. Most high schools we've found between 300 and 400 ton, and they're really using they're going to be using 450 ton at this point. They're already over 350 at this time of the year, and we still have a good amount of heating season left, even though it's a beautiful day today, but there is months to go.
As I recall, that the St. Johnsbury School is a K-8 school, and then there's an option for high schools elsewhere, on around.
Yeah.
I don't think so it's a big. I think it's 700 students. That might give you some hint, but we can get that figure back for you on square footage.
It's right around. It's going to be over 140,000 square feet. Wow. I think. If I remember correctly, it was more like 160 or something like that. It's a much larger school than I thought initially when I thought it was smaller, but there's a lot of sort of outcroppings on that buildings and additions.
It has the look of like an old high school that's been converted for use in the K-8. I don't know if you agree with that, but it's a big building. Okay, one other. It says, how much did you work with the schools to reduce their demand? And did you improve the heat emitters, for example, in some of these schools?
So it's two different. So in the St. Johnsbury School, that was driven all through Kohler and Lewis. So the interior, I'm not sure what they did there. We were really just a boiler plant, or really just a boiler maker in this case, the boiler and silo manufacturer, installer. And so that was our scope there. I don't believe that they did a lot of upgrades. There was quite a bit of remodeling throughout the school, and so there would have been some new emitters and some new distribution things in there. There was some controls upgrades by control companies. So I will tell you that the increases for everything were really generated by the COVID thing. I mean, it's just everything was on 100% outside air, which they never do before, have never done before. So in the Campton School, however, they removed a tremendous amount of valves. There was very little control, and so they put DDC control in there, and they improved the delicate controlling of each zone tremendously. I mean, I think that they put in 60 valves or so throughout the facility to really tightly control all the different operations. And they've obviously yielded really good results, even though in them they didn't hardly close school. They only had a few days here and there for COVID, but their school was in full operation all winter long.
Okay, so what do you think the return on investment is? This is from Dick here. What's the return on investment of these boiler systems?
Unfortunately, I cannot say that for these two schools here, because we are really just a subcontractor. Most of the paybacks when we sell boilers directly are between 5 and 8 years. So it's not. I don't sell these contracts because of the larger contractors are at stake, so they put our numbers in, but I don't have access to these larger numbers. So for us, when we sell them directly, comparatively, we would have a 5-year payback. That would be, you would have to figure out what your return on investment there is, but that, it's not too shabby. It's not a great investment in terms of energy. You can probably do better with certain things, and we always encourage people to do energy savings first, especially when you are having a COVID year where you have to ventilate so much. Everybody wished they had done energy savings to be able to reduce to reduce air and things like that. So or air exchange, I should say. But in this case, there was little, there were some changes done at Campton, but fewer changes I expect over at St. Johnsbury School.
I guess, well, Campton, you can
School.
say Campton was EEI, which is an
Right.
energy performance contract, and we don't always know what the terms are, but generally
No.
they are the goal is to have the energy savings pay for a 15-year note, so that if they're not spending any additional money per year, they've been successful. It doesn't point directly to the energy cost savings, but sort of an indirect loop there. Whereas somebody that just buys the boiler outright has a more direct means of understanding what that ROI is. As Mark said, we're selling a service to a GC that's all part of a bigger contract.
Yeah.
I was going to say that the fuel savings in New Hampshire, because of thermal RECs, the PDCs, or the dry chips that we have, are about the same as buying oil at 80 to 85 cents a gallon. And that again with like a net profit of about $16 on the thermal RECs per REC, that is. And then if you were in Vermont, they don't have thermal RECs, so it's closer to $1.30 a gallon. But that savings alone is a pretty significant savings over oil. And then you continue on with other improvements, and you always have to compare it to the price that they would have paid just to put in a brand new oil system because they needed replacement or whatever. That's often the case, such as at Campton.
Yeah. It's not early on, and this I can address this a little bit from our philosophy. Early on, we did a lot of installation that were undersized and really trying to maximize the dollar and the paybacks. And that helped with a tremendous amount of sales, of course, and that was fun to have all these sales. We have less sales now than before. It is probably related to the payback, I'd imagine. Also, we've had a period of pretty low oil prices for some time, so that is even further diminished, unfortunately. But nonetheless, even so, it's nice to get a payback, and it does sell better. But if you have to increase maintenance for that later on, you're really just telling a story that's not quite full. And so we've just found it better to come in with a realistic payback. So, even if it's 7 or 8 years sometimes, so we have even seen paybacks with 10 years. But it's more realistic, and it will actually really help in your operations as well. And so we've drifted that way, and maybe we don't get as many sales, but we also don't get as many service calls or warranty issues and things like that. So we've really drifted a little bit to the larger customers because of this event, because when we have larger customers, then we have a little bit more usage, and therefore we can still come in at a reasonable payback period.
Yeah, one thing to be said too is that if you compare these two projects, they both have something similar, is that they have a new outbuilding that had to be built in order to contain the biomass boiler system and the backup in the case of Campton. And other schools such as John Stark and even the sister school, Plymouth High School, those were installed in existing areas inside the building, some in existing boiler room most of the time here. And so it's a little bit easier to cost justify something. You don't have to build all that extra building and then put in buried pipes and so forth. So you're usually better off if you can get it in the building, but very often you can't.
Yeah, it's a little bit. I mean, some buildings, some schools put a lot of value at adding these buildings because maybe they get that little storage that they wanted for the ball fields. Other people want it for safety. They don't necessarily trust that, maybe they want to have the delivery truck further away from the building or things like that, or maybe they don't have an access road where they can really get to the building. So there's so many different considerations that you have to really individually address. It takes a tremendous amount of experience, frankly, to do what we're doing, and of course, some decisions are not so difficult to make, but it's nice to have, a few years of experience by now to help the customers along with a good decision. And it doesn't take that much. You don't have to get into massive calculations to really provide a little bit of experience and good know-how for your customers to make really sound decisions. And most of the time we're actually doing it with engineers. So we are much more versed in helping engineers than end consumers or customers at this point. At this point, really, most of our work is through specifiers, because larger projects always warrant a larger engineering or specifying team. So it could be a group of people, it could be you know, an engineer-driven project, but it, you know, if it's more industrial, probably just an engineer-driven project. But if it's more consumer-oriented, such as you know, with a school or things like that, there's a pretty large team of people are making decisions and going along. So it's easy enough to give some advice and make some recommendations in the right direction. And people have been pretty receptive at, for, you know, as long as you're providing good ideas and you're not overreaching.
One more question. Are we designing with Schmidts all the time now? In other words, how do we choose boilers these days?
No, we're not. So Schmidt is certainly on the large scale the boiler that's available to us right now, but so we're exclusive on the large side. Once we get over, I think, what is the size? I think once we get over like 3 million BTU, so we pretty much stay exclusive with Schmidt. It also happens to be that, you know, we have other manufacturers such as Froling and Okefin and even Viessmann still that are still available, and we don't have exclusivity agreements with them, but with Schmidt we have an exclusivity agreement on the large scale, but also only to a certain size. So after 6 megawatts, we also don't provide services exclusively for Schmidt as well. So we then have other partners that can make even larger boilers. Now, if it needs 2 boilers, we could provide, you know, a package boiler still up to 6 megawatts. But after that, then it really gets into the Vinci brand or even other brands, and there's even some Americans. And so we're not really exclusive on all things, but we are exclusive in certain ranges of boiler sizes. But if they can't supply it, then we don't have to be exclusive. So in some cases, there's specialty fuels, such as really fine sawdust, where people want to have sawdust, and some of the sawdust or some of the waste products cannot be burned in, for instance, a Schmidt boiler. But Vinci makes really good boilers for sort of waste products. That's their specialty. And so certainly, if it's really specific of a fuel, we will find the right manufacturer to do it. And our philosophy has been really that we stay agnostic on this whole issue and try to provide the customer with the best solution. And you know, and then of course uphold our agreements in terms of with Schmidt or with Tarm, who's repping the Froling boiler. They've been really great suppliers and really good distributors, and Okefin has done also a really good job. So we quite like them, and we recommend them as we seem fit for the owners. And you know, Froling and Okefin make really good residential units and even light commercial units as well. But I would not, you know, if I'm getting into the school, then probably a pretty heavy duty boiler at that point, running thousands of hours. So we, you know, that's probably more when I'm drifting into Schmidt, even though Froling, there's a boiler right in between that has a TM. And so that one is a little bit where I have to make a decision. Can that be used, or can the, you know, the Schmidt be used? So there's a, you know, we get to a point where there might be a slight bit of conflict, and that needs to be worked out. So, but we're not just using one vendor. We're really pretty agnostic and have been pretty successful at staying pretty open to that.
Okay. Well, we thank everybody for attending. And if you
Perfect.
have any questions, you can send them to me. You can, I will pass them on to Mark and get you answers. Slides, somebody asked about slides, and we can get you some copies of some of those pictures or whatever you're looking for. So again, thank you very much for attending. We've got applause coming in from Maine. We appreciate that, Maine. And thank you for everyone at Kohler and Lewis for sitting in. That might have been a big group there. Okay, Well, we will
Sure.
end this now.
Thank you.
Mark.
Bye-bye.
Bye.